Right? What is similar in these equations? We have x over u infinity that, if you remember, is a time. It's the time in which the piece of fluid is seeing temperature. Alpha is thermal diffusivity, and nu is kinematic viscosity, but in reality it's a diffusivity too. It's diffusivity down the diffusivity for transmitting shear forces by viscosity. Now, if you remember, when we did our study of the boundary layer, this study, we had this condition. In the thermal boundary layer, under these conditions I have here, for Prandtl much less than 1, what is the velocity? What velocity did we assign to the fluid inside the thermal boundary layer? Exactly, u infinity. So if I were at this point, and this is my viscous boundary layer, right, is something like this. And this is u infinity. Right, all inside here is u infinity. Right? Now, if I'm inside the viscous boundary layer, I cannot say that, right? The velocity is a velocity. So velocity varies in viscous boundary layer, and in viscous boundary layer, velocity varies more or less linearly. So that's the main reason. In this one we have a 1.77 because velocity is constant, and in this case we have a 3 because velocity is not constant inside. In this case, if I do y thermal boundary layer divided viscous boundary layer, that would be 1.77 square root of alpha x over u infinity divided 3 square root of nu, and this is 0.6 Prandtl to minus 1/2. Right? All I'm doing is comparing the thickness of the two boundary layers. So what do we learn here? We learned a number of things. One, we learn that if we say that the thermal boundary layer is much bigger than the viscous boundary layer, right? That was our initial hypothesis. I just said, let's assume this case. There are two extreme cases. Let's start with one. If this is much bigger than this, what does it say of Prandtl? Prandtl is very small, and a very small Prandtl, right? And actually, for this to be 0.1, this guy needs to be 0.01, very small. This Prandtl value is much smaller than 1, which is something I've been telling you, but I wasn't showing you why, right? So Prandtl has to be much smaller than 1, and this means molten metals, metals, and plasmas. Muddy people love molten metals, right? We weld and we cast, we do all kind of things. Some chemie people care about molten metals. That's what you use to cool nuclear reactors in submarines, right? You use molten sodium, things like those. Now, other take-home lesson. You see that it's Prandtl to the minus 1/2 here. This Prandtl to the minus 1/2 is typically associated with correlations for Prandtl, molten metals, and things like those. So if you now go to the book or a heat transfer handbook, you're going to see that most correlations are not with Prandtl to the 1/2. Typically it's to the 1/3. That is something I want to do now with you. But when the 1/2 appears, you're going to see that they say that the correlation is for molten metals, right? And I care so much more that you have a sense, a fighting chance of what's going on, than just to say, oh, I'm going to plug and chug. Because if as a chemical engineer, you're calculating a heat exchanger, and you get a correlation that has Prandtl to the 1/2, you should immediately stop and say, what's going on here? Because it shouldn't be. You don't just plug the Prandtl to the 1/2 blindly, I would hope, okay? And if you have to calculate something you have never seen, you would say, okay, is this a molten metal or is it a viscous fluid like oil? And then you would know that the correlation would most likely involve Prandtl to the 1/2 or the 1/3. Equal or bigger than 1. This is the one you care about. But it needed some effort to build up to it. So here we have our beautiful plate. So this is my thermal boundary layer. This other one is my viscous boundary layer. Okay? Now I flipped it. They are not so ridiculously different because I don't have room in the board. But what I'm saying is viscous boundary layer is much bigger. Of course, it's the case of oil. Because oil is very viscous. It can transmit this viscous effect very easily. Molten metal is not very viscous. Now, molten metal is an awesome conductor, but oil, I'm not too sure it's a great conductor. So in this case, the boundary layer is flipped. And what the big deal, right? So this is what happens. Here comes the cool graph. So make room for it. I'll make it straight. All right, so let's pick this point x, right? This is our x-axis. This is our y-axis. At this point x, I'm going to make the viscous boundary layer. So this is y here, and the viscous boundary layer is going to be something like this. You see how I'm building this? Please, this is the way you should do it on Friday, right? So this is going to be U infinity, right? Because in this graph, the axes are flipped. This is the thickness of our viscous boundary layer. According to this definition we have, that is the tangent. And the viscous boundary layer is going to be like something like this. And in the box, you're going to see these beautiful lines here, right? Are you with me on that one? Because nobody disagrees, I'm going to take it as a yes. Okay, but look at this. Now I'm going to do the thermal boundary layer. And in the thermal boundary layer, we said this is the plate is at a constant surface temperature, Ts. And by the way, something I have never asked, but I want to plant a thought in your mind. If we were to have molten metals and not a constant temperature plate, but a constant heat flux plate, what would be the boundary layer? Just going to leave it there, but it's an interesting question. But in this case, we're doing a constant surface temperature boundary layer. And now, at this position x, the thickness of our thermal boundary layer is this. Here is T. This is going to be distance Ts, and it's going to go to T infinity here. Right, and we go with our tangent, which that's a good reason we define it. And this is going to be our temperature boundary layer. All right, you see, viscous boundary layer is thick. Temperature boundary layer is relatively thin. This is the case of chemies. So this is the one you care about. Now, there is something called the Reynolds analogy. And it says, something I mentioned to you with words before, that if Prandtl is 1, right, the two boundary layers would be the same. And the solution to both equations is exactly the same. So you have Fourier law of heat transfer, and then you have Navier-Stokes. And the solution you can prove in math is the same. All right? So that's what is called Reynolds analogy. So when YCT equals YCV, then solution to equations is the same. Right? And this happens when Prandtl equals 1. Okay. And the other thing is, and what is the solution? Okay, let's talk about Prandtl equals 1. For Prandtl equal 1, we have YC T equals, what would be the formula? So it's always, we have this square root of something that is a diffusivity times a time. This is a time. The diffusivity here, I'm going to put alpha, right? But it's kind of a moot point that Prandtl equals 1, because alpha and nu would be the same. Prandtl is the ratio between alpha and nu, right? What should I put here in front of my square root? What number should I put? That's what matters. This part is easy. What number should I put here? You have two choices. No. So I have a suggestion for 1.77, but that is not, because that is when the velocity is constant, right? When we have the constant velocity through the thermal boundary layer. But this is not the case. On the other hand, because of the Reynolds analogy, what we are saying is that a thermal boundary layer behaves, it has the same solution as the viscous boundary layer, right? What goes here is a 3. You follow me? Remember that in the previous analysis, we said that inside the thermal boundary layer, velocity was always U infinity, except in a thin layer. But now we're saying, no. Now this is smaller, so the velocity is changing all the time. You see how as I move up this boundary layer, the velocity is also changing? You see that? So in this case, and for Prandtl equals 1, is this is exact. And for Prandtl bigger than 1, we have YCT is more or less same thing. Oops. It's more or less the same. Okay. You see. Okay. Here's a small difference. You see, I put UC here. If Prandtl is bigger than 1, as it is this case here, I put a UC. Where would that UC be? What do you think this characteristic velocity is? So here, at this point, you see our thermal boundary layer. Our thermal boundary layer has this maximum velocity in it. It's not U infinity, right? Because our thermal boundary layer is very close to the plate. You follow me on that? Nobody tells you that straight. And I know you are dying to know. But so here, what you have this here, this is this characteristic velocity. The thermal boundary layer happens very near the plate for you chemies, not for the Matties. The Matties can go to sleep, Facebook, whatever. But the chemists, stay with me, because for the chemists, this is what you care. So the velocities, the temperatures in the boundary layer of oil and all those things you guys like, okay, those temperatures are very close to the plate, right? And the velocity is not fully developed then, right? That's why I put, you see, thermal boundary layer is does not reach U infinity. Compare these similar triangles A, B, C, and A, D, E, and we would have DE, this part, divided EAE, right? EA here, divided this is the same as this side divided this other one. I'm going to put it in a sign. So let's see, DE. What physical magnitude is DE? U infinity, thank you. What is EA? Thank you. We're kicking some butt here. Okay, thank you. BC. UC, that is the one I didn't know. You see? Is UC. And now we have CA, that is what you mentioned, the thickness of the... Okay, so what this says is that UC is U infinity times YCT over YCV. Now, in your notes, you have every steps of the derivation. I do not pretend that you're going to do all this yourselves alone, or that I'm going to show it to you very quickly right now. Well, I will show it to you quickly, but it might not be trivial on first attempt. But from these triangles, I got what UC is, right? And we have this YCV, the thickness of the viscous boundary layer, and that one we know. And this is funny because fluid flow affects temperature. Fluid flow brings temperature in and it takes temperature out. But temperature has very little effect on fluid flow, right? So the problem is kind of, to some extent, coupled only one way. So the calculations for fluid mechanics, so we needed fluid mechanics to do heat transfer, but you do not need heat transfer to do fluid mechanics. And that's how the class sequence goes. So YCV, this is just pure fluid mechanics, was 3 nu x over U infinity. So if I now start replacing things here, I would put, I would go to, where was YCV? YCT, where did I have YCT? Here, YCT. I'm going to do this square. So I can say YCT equals 3 square root of alpha x over UC. If I do this square, I end up with YCT square equals 9 alpha x over, and UC was U infinity YCV over YCT, right? I'm going to bring this YCT up here. We can divide this by YCV cubed, YCV cubed, and we're going to end up with YCE, YCT, or YCV cubed is 9 alpha x over u infinity ycv squared, and this is 9 alpha x over u infinity, and we discussed this already, u infinity. So we would have that uct over ycv is Prandtl to minus 1/3. All right. So what was the point of all this? All the plug and chug, anybody can do it. Anybody can do it. It's just find the letter, the Greek letter, whatever, go to a table and plug it in. Where does it come from? So we did this thing that I am fully aware that might not have been like immediately obvious, but what did we do? No differential equations, neither partial nor elementary, ordinary. We just use our concepts. We use some things we knew from the semi-infinite solid. We adapted that for the viscous boundary layer, in which I didn't prove you. That number 3, this number 3 here, that was done by Prandtl's student Blasius. Blasius was a super cool guy. So he spent all his PhD solving the differential equations, and he got that 3, right? You know what he did when he graduated? He said, I'm never again doing any of this again, and he became a high school teacher, right? But you have the 3. Isn't that a happy life for you, right? So we use that. Now we start to put these things together with our understanding about the boundary layers. And guess what? We came to the point that this ratio of boundary layers, and this is for, in what conditions is this? What conditions is this? Laminar, thank you. Laminar, what else? Yeah, flat plate, I like that. This is, okay, I'm going to do, you mentioned Prandtl. This is for Prandtl, more or less equal or bigger than 1, right? You mentioned flat plate, right? I'm proving it for flat plate. But the cool thing is that if you do this smart work, actually, it's the gift that keeps on giving. This is good for, also good for most other geometries. If I have the thickness of the boundary layer, how can I calculate H? You'll be telling this to me on Friday, by the way. K over YCT, right? Is conduction through a thermal boundary layer. Conduction through a thermal boundary layer. K over YCT, YCV. I'm going to multiply and divide by YCV. And what do we get? We get H is okay. So we have YC of velocity over YC thermal, right? This was Prandtl, in this case, velocity to the minus 1/3, right? Sorry, to the plus 1/3. There you go. This is what we just derived. The plus or the minus is depending on what ratio we're considering. I flipped it there. So we are going to end up, and YCV is 3 square root of nu x over u infinity. And this gives us H is K of so I have just calculated H here. That's typically what you want, H. And what do we see? Do you see that it's 1 over square root of x, 2? Very similar to what we did before, that was good only for molten metals. So the good news for you, chemists, is that much of what we learned for the molten metals, yeah, it's true for you too, with oil and all those funny stuff you use. Okay, in any case, there's one more twist, right? Nobody tabulates H. People, how is H tabulated? How is H put in the box? Anybody remembers? H is tabulated in the form of the Nusselt number, right? So you're not going to see tables of H. You're going to see tables of Nusselt. For example, what we have there, right? So if we do Nusselt tabulation is Nusselt, in this case would be Nusselt of X, and is this local or average? Local, thank you. Is Hx over K, and in this case is would be Hx over K. So is H, I have it, over K, this K goes away, and the X comes on top, and I'm going to have this 1/3 square root of U infinity X over nu, Prandtl to the 1/3. This looks like the jumble of things, but if we remember, this is the Reynolds number, right? This would be Reynolds X. So we have in this case, Nusselt of X equals 0.33 Okay. So this is equation 7.21 of the book, to which they arrive after solving the Navier-Stokes equations. Look at this. This is a tabulation you're going to find in books. And you might have a vague sense of how we landed here. This Prandtl to the 1/3, right? What does it mean? Is this correlation for molten metals or for oil and air and water and that stuff? Oil and air and water, because it's to the 1/3, right? So this is for Prandtl bigger than 1. Here we have the Reynolds number, right? And this is still for laminar case, right? And here we have a coefficient, and this coefficient, right, can come from sophisticated equations. Sometimes it would come from experiments. Right? In this case, this 0.33, you know where it comes from. It comes from playing with the thickness of the boundary layers, as we have been doing it. And it can be traced all the way back to the heat conduction across the boundary layer, right? Whether it behaves as a solid, and we use the semi-infinite solid, or is more or less similar. Instead of 1.77, it's a 3, and it is the case of heat conduction when you still have advection inside the boundary layer.